telling me that we are going live right now, which is very exciting. And I am super excited about today's episode in particular because it's about quantum computing, which is kind of this brain, I can't say the word that I want to say, but it hurts your head a little bit when you think about it. Quantum physics in general is kind of this rabbit hole that a lot of people, especially in the crypto space, have been going down recently after the news that apparently Google has achieved quantum supremacy. Now, what does that even mean? What is quantum computing? How could this possibly be a danger to the crypto space, in particular Bitcoin and any cryptocurrency that uses a certain type of cryptography to protect private keys? So we're going to go into that in detail and talk about all of this. But first, right off the bat, I'm going to welcome to the show Eric Dennis. Eric, it's so wonderful to have you here.
Thank you. Happy to be here.
It's so great. So, Eric, you're the expert that I brought onto the show today. I've been wanting to cover quantum computing for a while now. And you're one of my closest friends who just also happens to specialize in quantum computing. So you did your PhD in physics, specializing in quantum foundations and quantum computing. So you are a wonderful resource for me in particular to be asking all my dumb questions to. And I really appreciate that. And now we can ask you dumb questions live on the air so that people can understand this, and then maybe ask you some more intellectually in-depth questions and get your perspective on what's actually going on in this quantum computing space. So right off the bat, just so that you guys have a little bit of a background in what's going on. Oh, the live is going on. You guys can see us all right, right? All right, so the chat just went a bit strange. So what actually happened was this week, Google, this paper got released that apparently outlined how Google has achieved quantum supremacy. Now, what does that mean? It basically means that we've been trying to figure out quantum computing for a long time, and it's this largely theoretical space. And scientists have been trying to figure out how we could use quantum computers, which operate quite differently to classical computers that we understand, how we could use them for different functions in our lives. And quantum supremacy refers to when you finally you do a test of you target a very specific problem, and the quantum computer is able to perform this task in a more reasonable, much better than a classical computer would be able to in a reasonable time frame. So that's basically the essence of what's happened. They created this very specific problem, and this quantum computer that was using, I think it was 53 qubits. So we'll explain what a qubit is in a second. Meant to be 54, but apparently one of them conked out or something. So it was able to perform this task a lot better. Now, there are lots of caveats in quantum computing, like you have to be able to verify the accuracy. There are huge margins for error with quantum computing at the moment. So we'll go into all of that. Eric, I'm going to hand over to you, and let's just first of all give people a little bit of background of how quantum computers are different from classical computers.
Sure. So let's start with what is quantum mechanics. Quantum mechanics is this theory that came up around 100 years ago to try and describe how atoms and molecules and subatomic particles work. And it's a very successful theory, but it wasn't until the 1990s or so that someone figured out that if you built a computer whose basic components, so for the basic component of a classical computer is a bit, it's either on or off, it's either 0 or 1. If you built a computer whose basic components were quantum bits or qubits, and you could have not only a couple, but a large number of these qubits, and these qubits could exhibit these quirky quantum mechanical effects, which you don't see in normal life and you're not used to. If you could build one of these computers, it turns out, we discovered in the 90s, that you could crack one very specific problem. You could crack the cryptographic protocols that protect a whole bunch of our transactions over the internet and are also the basis for cryptocurrencies.
And what is the name of that specific type of cryptography? like RSA or?
RSA is the particular algorithm that it was shown in the 90s that, that a quantum computer could crack. And it's subsequently been shown that other similar algorithms like elliptic cryptography can also be cracked by a quantum computer.
So let's just right off the bat mention that, and we'll go into Bitcoin sort of at the end once we've talked through how some of this works. Bitcoin is protected by two different types of cryptography. One of them is the sharp hashing algorithm that we all know, and that's basically what the miners use. But then the cryptography that is used to protect your private keys is elliptic curve cryptography. So that gets a little scary when we start saying that, you know, we now have quantum computers that could theoretically crack that. Now, let's go into this whole theory versus reality situation, because a lot of quantum mechanics and quantum computing is largely theoretical, and it's incredibly difficult. And basically what Google has achieved is this mind-boggling, astounding technological leap. Like, it's huge that they've managed to get a computer going, achieve this quantum supremacy in this particular very narrow problem-solving area. But you know, quantum entanglement, which is what happens when you add qubits to the mix. It's not like Moore's law, right? That's my understanding, that it's not like this thing will just start getting easier and easier. Like, the more qubits you add, the more complicated this gets, and the more, like, the harder quantum entanglement gets. So kind of explain that a little better.
Yeah, so the idea is that for certain problems, and really there are only two, these are two classes of problems. There's the one class which has to do with cryptography, and a different class which has to do with simulating other quantum systems, which we don't care much about here. But in either of these two classes of problems, as the problem gets bigger and bigger, so as you want to break a bigger and bigger key in the cryptographic space, it takes a normal computer, a classical computer, exponentially longer to break a longer and longer key. But a quantum computer, the discovery all the way back in the 90s was that if you could build one, it wouldn't take exponentially longer. It would only take, polynomially longer. So something like linearly or quadratically longer as the key gets bigger and bigger. And so what that means is that if all we had were classical computers, it's pretty easy, as computers get better and better over time, to just increase the size of your key. And you could increase the size a little bit. You could just double it, or make it 50% longer, and that would give you an incredible amount of extra protection. But if there are quantum computers out there, and they don't have to do exponentially more computations to break a longer and longer key, then it's not effective just to increase your key size, and the whole kind of paradigm of that cryptography kind of goes away. Now,
so sorry, go ahead.
Yeah, well, I should mention one caveat to begin with is that while there are these certain types of cryptography like RSA or elliptic curve cryptography that a quantum computer can break, there are other forms of normal classical cryptography that apparently there's been no known way for a quantum computer to break those. So those other forms of cryptography, I don't know if there are any coins out there today which exploit those forms of cryptography, but in principle, it would be possible to build a cryptocurrency based on those other forms, which would be much, much easier, for instance, than trying to build some quantum computing-based cryptography and have a quantum computing-based cryptocurrency. So there could be potentially relatively easy fixes for this problem, even if there were this big quantum computer that can hack into the current cryptographic routines.
So what would you say about the claims that the press are just going wild right now? And there's all this hype. Like I read this article by this esteemed cryptographer, one of the most well-known people in the space, Scott Aronson, and everyone's kind of chastising him because when D-Wave, which was like in the 90s, started looking into quantum computing, and he was like, guys, this is overhyped. But now this Google thing has happened, and he's like, guys, get hyped. But he kind of explains that, it's not his duty to to go in the correct direction of the hype meter that people want. It's to be correct. And D-Wave, he says, was this overblown thing. Maybe we could talk about that a little later. But he says that this is really an astounding feat and we should be excited about this. That being said, I'm reading all these articles from like New York Times and the Washington Post and all these supposed good journalistic places. And they're saying things like, guys, we're going to be able to create climate predictive models that will predict with absolute accuracy the weather. And we're going to, ruin all cryptography on the internet. And we're going to be able to process every little bit of data in this completely, like they're kind of talking about this as if this is this panacea and this is going to solve everything. Like, I think we should address the fact that quantum computers and classical computers are not interchangeable. Like, it's not just that one of them takes a long time to do certain functions. They intrinsically are different and serve different purposes. So I think a lot of people have in their minds like, oh, well, normal computers, they're too slow for certain things. That's why we need quantum computers, because it'll just speed up the functionality of my normal computer. And that's not really how it works. Like, quantum computers, I mean, it seems that they have this very narrow area where they're useful. And although it's astounding the feat that has been accomplished with Google, it's still this incredibly narrow scope. And it's not like we just, times by 100 the capacity of normal computers. They're not interchangeable in that way. So what do you think about all the claims from journalists saying like, we're going to have completely predictive climate models and all of that stuff?
Yeah, those claims, any claim about some super predictive climate model based on theoretical future quantum computers, much less what Google has demonstrated now, that's total hype. There's no basis for that. As you said very rightly, there are essentially two very, very narrow problems that quantum computers solve that they're much, much better than classical computers on. For essentially any other computational task, the classical computer is way, way better than a quantum computer because it's 1,000,000 times cheaper, and it would be much easier to just get a faster, higher storage classical computer than use a quantum computer for that task. So again, there are these very two specific problems: simulating quantum systems, which isn't really relevant here, and cryptographic and cracking certain cryptographic codes.
Right. So it does seem like there are a couple of caveats with all of this hype we've been seeing. As you mentioned, one of them is the very narrow scope of this. And then the other one is what you've already talked about how possible is this? How feasible is this? And it's taken since D-Wave. So it took us, what was it, 20 years to get to 50 qubits? Is that correct?
Sure. Yeah. I mean, it's ambiguous when you start the clock, maybe sometime in the late 90s when people started really looking into building a quantum computer and not just theorizing about one. But sometime around the late 90s to now, we've gone from a couple qubits to now around 50 qubits. Right. It's way too small a time to say that anything like Moore's law with high probability applies to this. Moore's law could apply. It could be that, every year, a couple of years, they're able to double the number of qubits they have. But it could be the case that that doesn't apply at all, and they hit some ceiling and it just stops working. Also, there's one really important distinction here. So there's what Google has shown they've built, which is a quantum computer of pretty reasonable accuracy with 50 qubits in it. That's what. And
can I just clarify the reasonable accuracy point? Because I think that's really important. Then we'll continue along there. So one thing in my reading that I noticed about this is it seems quantum computing is incredibly unreliable because of the quantum state, that there are no certainties. Like, I mean, you explain this a lot better than I can, Eric, but it seems that there are no, like, it's not like it spits out this definitive answer. A normal computer will spit out like 1 or a 0, it's like black or white. There's kind of this binary. Quantum computers don't exist in this binary. So they work in this probabilistic manner and nothing is really definitive. And what we found is that there's huge error margins, especially they created computers.
Yeah, hold on there. Hold on.
Okay,
I want to cut you off before we get too far in there. So it's true that the results of a quantum computer typically are probabilistic. That's really not the thing that differentiates them from normal computers. That's not such a big deal. You could actually have probabilistic classical computers, and they would have the same kind of limitations. The real difference in quantum computers, it's a little hard to describe because it gets into the heart of the weirdness of quantum mechanics. But suffice it to say,
it does my head in.
we can get into that as much as you want, but suffice it to say for now, the quantum computer is just a much, much more physically complicated object than a classical computer. And what that means in computational terms is that correcting errors in the computer is a much, much subtler task for a quantum computer. So you have errors in a quantum computer just like you have errors in a classical computer. You know, the normal example people use is like a little cosmic ray comes down and zaps your hard drive, and bam, one of the bits in your hard drive flips from a 0 to a 1. You know, and if that was a particularly important bit, you know, that could screw up your entire, you know, retirement savings or something, right? But classical computers have a really easy way of correcting those errors. If you want to store one bit of information, so let's call that the logical bit, the actual information you want to store, then just instead of using a single physical bit, you use maybe 3 or 4 or 5 or 10 or some, you know, relatively small number of physical bits. And if you want to encode a 0 in your logical bit, what that means is you just take all the physical bits and you set them all to 0. That way, if a cosmic ray comes down and zaps one of them, and you go out to read the bits later, you'll see that 9 of them are 0 and 1 of them is 1. And you say, oh, okay, that one obviously is the odd one out. It's been corrupted. I'll just flip it back to 0, and I've now corrected my error. So that's a very kind of elementary error correction procedure, which, you know, normal computers use and everyone's known about for a long time. With a quantum computer, because of the quantum mechanical nature of these bits, the nature of the errors themselves are more complicated than just a single bit being flipped. And it has to do with how the quantum computer kind of explores the entire space of the possible configurations of all of the classical bits. We can get into that if you want, but the upshot is that it's much more subtle and complicated to protect a quantum computer against errors. In fact, that's what I did my own work on in quantum computation. Some of the original ideas for those error correcting schemes, I worked on one of those ideas that was pioneered by a guy named Alexei Kitaev. That idea of how do you correct errors, that became essential in quantum computing. And once it was shown that even though it's a little more subtle, you can do it. You can correct the errors. You can have the quantum mechanical analog or the quantum mechanical equivalent of one of those error correcting codes where you use 10 bits to encode your information instead of 1 bit. There's a quantum version of that which works. And that is the basis on which we say that at some time in the undetermined future, it may be possible for a quantum computer to run the kind of algorithms it would need to run to crack the cryptographic protocols. And so the essential point I want to get at is that the thing that Google has apparently, by this kind of leaked paper they've done, the paper hasn't even been confirmed yet, but assuming this leaked paper is legit, the thing that they've shown,
it was leaked, like, just before you say that, is to explain why that is. So this just appeared, NASA put this out and then immediately pulled it back. And I believe there were NASA researchers working on this, which is why they probably put it out, but apparently was not ready for release yet. And people are speculating it'll be like a month or something before this will be released, although no one really knows. So just to clarify that. So go ahead, Eric.
Yeah, exactly. So it seems like it was an accident. The NASA guys just accidentally released it for, like, you know, an hour or two or however many hours. But the idea is that once you kind of establish that error correction works, that's kind of the basis for the idea that sometime in the far future, probably, if we actually wind up being able to build that quantum computer with many, many more qubits, then it will be able to crack RSA or elliptic cryptography. But as of right now, the 50 qubit quantum computer that Google built is nowhere near cracking any kind of cryptographic protocol like that.
And so the difference between where we are and where we are then, I just want to explain that as well. Sorry to cut you off there. What were you going to say?
So the difference is, so right now they have 50 qubits, and the rate of errors are technically 53 qubits, and the rate of errors they're experiencing on those qubits is something like they have 99% accuracy, or a 1% error rate on each of the qubits. And it's been estimated to do something that is actually a real problem, like cracking the cryptographic codes. That's going to require not 50 qubits, but something more like 1 million or multiple million qubits. And the error rate also has to be probably an order of magnitude better.
Right. And so let's just kind of distill that for people watching at home. So we do say that, yes, and kind of also to transition into the crypto world. When I say crypto, that's confusing in this sense, transitioning into the cryptocurrency world, and well, cryptography in general. So where we are right now, 53 qubits. And people are speculating that, well, the problem that Google is able to solve will affect elliptic curve cryptography. So we know that Bitcoin would be affected by this if they can get this system up and running. But the barrier to get from here to there is going from 50 qubits to thousands of qubits in order
actually
to
millions. Probably millions.
So 50 to millions of qubits. Correct. And quantum entanglement of millions of qubits, which is incredibly hard to achieve. But on top of that, it's not just getting them quantumly entangled, which is a feat on its own. It's getting the error rate down, which is orders of magnitude. They have to get a smaller error rate than we currently have, orders of magnitude smaller, in fact.
Well, probably one order of magnitude, but yes.
But just one order of magnitude, totally fine.
Just a factor of 10. That's
just a factor of 10. So it seems like, I mean, there is a risk. It seems like the quantum computing realm, because it specifically will target cryptography, a certain type of cryptography, and include in that it's RSA, which protects the internet, and elliptic curve cryptography, which protects our private keys in Bitcoin. It does seem like there is an issue there if this technological advancement continues, but we have a long way to go to get there. You know, this is not something that is going to be happening in the next 10 years, 20 years, maybe even. And a lot of people are speculating this may not ever happen because it's so far out of our range of capacity, our capabilities. What are your thoughts on that?
Yeah, it's basically like we've built a car, and the question is, can that car go to the moon? Right, you know, in 1900,
you shouldn't
built one of those.
Going to the moon when we're talking about cryptocurrency.
Better
than that.
Mixed metaphor there in the crypto world. So maybe we're going to Mars or something. But you know, you have your car that you're cranking. It has a crankshaft, and it's this old clunky thing from 1902. And you're thinking, oh, maybe someday this can get to the moon or Mars. And if you had an exponential increase in the kind of efficacy of the device over time, like in Moore's law, where every however many months, the power of a normal computer doubles. So it's doubling. If that really happens for quantum computing as well, then there is a proximate threat, but it's just that it's very hypothetical. Moore's law, no one talked about Moore's law until we had a whole bunch of data points, and we ranged over multiple orders of magnitude of increasing better and better normal computers. And we've basically accomplished 1 or 1.5 orders of magnitude of increase in the quantum computing world. And we're just not at the point, anywhere near the point where we can say we have high confidence that there's going to be a Moore's law. Of course, it could be the case.
Right. And that's something to keep in mind. We don't know, as you said, we just don't have the data, you know, and the history to be able to make predictions like that. It could be, as you said, that something similar to Moore's law happens and we just escalate rapidly and this tech moves really fast. And that's really interesting. Like sometimes when you get just a toe grip in something, that's all you need to just substantially increase development in something. Or it could be that we just don't get that. And this is a really complicated problem to solve. And we have no idea which direction it's going to go in yet.
That's right. That's right.
Yeah.
It's just a lot of uncertainty right now that is not really quantum mechanical in origin. It's just uncertainty about human progress.
Absolutely. So one thing we can say is that our Bitcoin is safe for now, and may always be safe. We don't actually know. At the same time, there are different companies that are working on what they call crypto resilient. Quantum computing resilient crypto, which is interesting. Like they say, well, we're going to build this and it's going to be resistant to quantum computing, which is interesting. But what happens to something like Bitcoin that uses elliptic curve cryptography to protect the private keys? Does that just disappear? Is that going to ruin Bitcoin forever? And I've chatted to Chris Pacier. You guys who watch my show know who Chris Pacier is. And his response was basically they'll need to have a hard fork at some stage. Like if it comes down to it and this is broken, you'd need to change how your private keys are protected. And it would be a bit of a nightmare, but it's also solvable. So it seems that at the end of the day, your Bitcoin's going to be safe no matter what. Like it's going to be annoying and cumbersome and probably really complicated to fix, but there is a fix. And that's if this even eventuates at all, if we even get from here to there, which is a big if right now. It's a big if. So, what are your final thoughts on this technology, Eric? Like, where do you think this is going? I know that you're very excited about this, but I also know that you're dismissive of a lot of this hype that some journalists are coming out with.
Yeah, so two things. One, like any kind of very sexy new technology, like, so-called artificial intelligence or any number of these technologies in history, there's a kernel of really productive, really great work, but then it's just inflated around it into this bubble of nonsense that just obscures what is really the good work. So this nonsense about, climate models or something based on quantum computers, you have to separate that stuff off from the legit stuff. And one more thing I want to mention is, what is this concept of quantum supremacy? Because the news event recently is really about, we've finally achieved quantum supremacy. And what does that mean? So really, it's just this particular 50-qubit quantum computer, this very incipient, early stage quantum computer that Google has apparently built. The reason they're saying it's achieved quantum supremacy, like you described, is that there is a particular problem, a computational problem, that this quantum computer can solve pretty quickly, like we're talking on the order of seconds, whereas a classical computer would take really long periods of time to do it. So it's maybe a billion-fold faster on a quantum computer than on a classical computer. But the funny thing about it is, what they did is they basically said, hey, Google said, hey, in the future, when they were planning this a few years ago, they said, we can see the point at which we, a couple years from now, which just happened now, get to something like 50 qubits. And what they did is they thought real hard about, hey, what kind of problem could we specially design? What kind of really weird, just very particular narrow problem could we specially design in such a way that the quantum computer can do it, but the classical computer can't? So they fine-tune this really narrow problem that has absolutely no application, it seems like. There's a little caveat, but it has essentially no application to anything what we actually care about solving. It was a problem designed such that a quantum computer could do it, but a classical computer can't. And the point of quantum supremacy is, even though that problem was very fine-tuned and it doesn't have any real practical significance, probably, it's still an amazing feat, and it demonstrates there are a number of people, some of which are kooky, but some of which are more rational, who for a long time have been skeptical of the physical possibility of a quantum computer. So these quantum computing skeptics, they've thought that maybe there's an unknown physical law or physical reason why a quantum computer will never be realized. And we'll ultimately discover that reason. But what this shows, at least it gives some evidence for, if it pans out, is that at least at this level, there is no physical law that's blocking us from creating a quantum computer. And so it's, in a certain sense, it's a discovery that has some importance about nature. It's kind of like the experiments a number of years ago, which showed the inherent non-locality of quantum mechanics, how you do something over here and it almost instantaneously affects something far, far away, much faster than light, for instance, showing that it's a property of the quantum world. And this shows this current progress that Google has made shows that there's something like that too in the realm of how much entanglement you can create. So we've shown before that entanglement is this weird non-local thing, and now we've shown that we can create it in a very controllable way on a scale that we have never done before, and that has this importance that at least computationally it blows away classical computers on this very narrow problem. And hopefully someday it won't be a very narrow problem anymore. It'll be something at least as broad as breaking crypto codes.
Absolutely. And just on that topic as well, just because you're talking about this very specific problem that was created. And it's also, I mean, quantum computers have this very strange nature where it's almost like the computer itself is created in the process of solving this and then immediately resets once it's done. Like, I've been reading about this. I don't know whether that sounds like gibberish to you. Maybe it does. Can you explain that in a little
well, there are probably multiple things coming together. So one is this idea just about quantum mechanics, that the observer creates the quantum reality, that the reality doesn't exist apart from the observer. This has been a somewhat controversial issue in the philosophy or the foundations of quantum mechanics, for the last 100 years. My own view, which I hold very strongly, is that itself is nonsense, that there is no evidence to do with quantum mechanics that somehow the observer is creating the reality. And with certainty, we know that there are formulations of quantum mechanics that don't require that kind of philosophical nonsense. So on the one hand, quantum computing, which overlaps a lot with these philosophical questions in certain ways, the computer is not being created by the experimenter or the observer. I think that's nonsense. But there are a whole bunch of just not as philosophically revolutionary or as metaphysically crazy sounding things, which the quantum computer does, which involves resetting itself or getting into one of these highly entangled states, which can connect all of these components in ways that we could never imagine in the Newtonian universe.
And by doing things like that, so when you have entanglement, because like usually, and we're going to have to do a whole separate episode on this, so I'm going to pick your brain and then I'm maybe going to do an episode about how quantum physics works in general for those who are interested. But the idea is that, normally light, it can move as a wave or it can move as a particle. When you have entanglement, things move a little differently. You can have like instantaneous movement, and that's what the entanglement, this is a super confusing realm. Eric, I'm going to need your help to kind of pass through all of this and put it in this easily digestible format. And we're going to have discussions about light particles. We're going to have discussions about qubits and entanglement and all of those wonderful buzzwords that are covering the newspapers these days.
No problem. Dial me up.
Absolutely. So one thing that I will just say as we're wrapping up here is that verification in these systems, as you've already mentioned, is really, really difficult. That when you're talking about a quantum computer solving a problem that would take a standard classical computer like 10,000 years to complete, so it's just not feasible for them to undertake this program. You have to have a way of verifying that. Like if you don't know the outcome, if you need a computer in order to compute that outcome, how do you verify that what it's come out with is actually correct? And so what they have to do is they have to have these problems that they can also do on these classical computers, so that they can verify and compare the outcomes of these. But of course they can't do it to the same extent of the classical computer. They have to do like one fraction of it and then kind of extrapolate to make predictions about what the final answer might be. Like it's this very vague area where we get into this realm where it's very hard to actually confirm certain things and verify things.
Well, yeah. So for the kinds of problems that they've specifically designed to test quantum supremacy, there's no easy way once the quantum computer performs its magic on 50 qubits, there's no easy way. In fact, there's no just relatively hard. The only way to verify its output would be to have a classical computer chug along for forever, essentially, to verify it. So what you can do, however, is as you approach that, so you go, 10 qubits, 20 qubits, 30 qubits, up to a certain point, you have enough classical computing power to actually verify that even on these highly tuned problems, that the quantum computer is actually being quantum, that it's exhibiting its quantum properties, it's getting these highly entangled states, and that it's doing it properly with sufficient accuracy, that it's getting the right quantum result. So you can check it for 20 qubits, maybe for 30 qubits, certainly for 10 qubits, and it's still unclear. There's still a little back and forth within the community about how much of this testing Google has done. Presumably they have done a good amount of this testing. So you kind of verify it on a smaller number of qubits, then you do it on 50 qubits, and you kind of use the evidence you've accumulated along the way that everything is working according to how you think it should work. And not only that, but you can do tests on 50 qubits where you tweak the problem a little bit. So you kind of, you force the problem into a problem that even though it's using all 50 qubits, a classical computer can actually compete with the quantum computer. It's as the problem kind of degenerates into a conceptually simpler one that a classical computer can solve. You put the quantum computer, attack that problem, it all works with 50 qubits, and you have confidence then that based on all of this evidence that it's actually working on the 50 qubit problem. And you can do certain things which give you some evidence that even on the full 50 qubit complicated problem, it's working pretty well too. It would just, to really verify that, it would take an enormously long time on a classical computer.
All right, so just to recap here, for anyone who just tuned in. So we have Google. They've apparently achieved quantum supremacy, which means that they have this specific problem that they've proven a quantum computer can solve solve faster and more effectively than a classical computer could in a reasonable time frame. They've apparently achieved this. It's a mind-boggling feat. However, it's incredibly narrow, and the usefulness of this is still up in the air. And then one other thing that we've discussed on here is that it's going to take, there are lots of barriers to people getting there. One, the very specific application that they've proven is to be able to hack RSA encryption, which is what protects our entire internet, and elliptic curve encryption, which is what protects Bitcoin and a lot of cryptocurrencies. Now, that's scary to a lot of people, but as we've said, long way to go before we get there. We have to go from 50 qubits to millions of qubits, and it's taken us 20 years to get in 50 qubits entangled. Then on top of that, we've got this error margin. At the moment, it's 99% accuracy, but as Eric says, it's at least an order of magnitude more accuracy that we have to achieve in order for this to become a useful system for us and to be able to crack these codes. So final summary, your Bitcoin is safe right now. Even if we are able to crack this, there are hard forks that could take place. There are migrations of your money that could take place that use something other than elliptic curve cryptography. As Eric said, this is a very specific application of quantum computers, and that they've been able to use and get working. And there are lots of different types of cryptography out there that are not affected. So on that note, as a final ending, there are some cryptocurrencies out there that are working on quantum computing resistant cryptography. There's IOTA, I believe, is one of them. There are some others out there, but at the end of the day, it seems like Bitcoin, it would be a solvable problem for Bitcoin anyway. So I don't think we need to worry. There's a huge amount of hype around this. We're not going to have completely predictive climate models generated by quantum computers anytime soon. That's just not the application of this technology. And this is a long, slow, incredibly expensive process. So perhaps, would you say that it's more hype than realism right now in the media? This is a mind-boggling feat. This is a huge technological advancement, and yet still it seems like it's being overhyped.
The rule of thumb in quantum computing is that there's always 10 times as much hype as there is substance. And it's probably no different for this particular result, although this, again, is a great result. And congratulations to the folks at Google who got it done.
Absolutely. So yeah, again, huge congratulations to all of them. This is an exciting field and I'm going to keep covering it. It's something that interests me. I've been in a rabbit hole this past week learning about all of this stuff. So I'm going to make a video that explains how quantum computers work. We'll actually look at quantum physics. Eric, I expect phone calls from me because I'm going to have a lot of questions, but you guys can expect that video soon. I did have a super chat here. I wanted to say a huge thank you to JR from Exciting World Cryptos. Check out his YouTube channel if you haven't already. He says, always quantum. Amazing. Thanks. I really appreciate your support, JR. It goes a long way to helping me keep this channel running. So everyone in the chat who's been here chatting, I love you guys. Thank you so much for being here. It's awesome to have you just hanging out with me and Eric as we chat about these things. And Eric, huge thank you for your time and expertise. It's always a delight chatting with you. You're one of my absolute closest friends, and it's so convenient that you also happen to be an expert in quantum physics because it makes episodes like this all the more fun. So thank you for being on the show.
My pleasure.
Yay. All right. I'll chat to everyone soon. Let me know if you have specific questions you want me to answer in my follow-up video, and go and have a wonderful rest of your night. Bye.